we look at beats, or interference in time. We have looked at interference due to sources separated in space, but what about the time component of a wave, or sources that are separated in frequency? Here we see a sinusoidal sound wave as a function of time. This is a 30 Hertz wave, and then we add another one which is 31 Hertz, so very close in frequency. And you can see that the red and blue curves are very similar, particularly when at near time equals 0. They get out of phase around half a second, come back into phase at 1 second, and so on. If we add these two, and get the superposition wave, we get the green curve. And one thing that jumps out at you is that there is an envelope over the high frequency oscillation the high frequency oscillation is around 30 Hertz, but there's a slow modulation of the amplitude. And this slow modulation of the amplitude is called a beat. We see that the maximum of the beat occurs near 0, and we get another maximum near 1, and another maximum near 2. And there's a minimum at half a second and 1.5 seconds. Let's look at this a little bit more mathematically. So we're looking at a fixed position, so this is only the time part that we're interested in. So the change in pressure as a function of time of the sound wave is equal to an amplitude, which is delta p sub m, times the sine of omega 1 times t. So that's one of the sinusoids from the graph above. Then we add in the second sinusoid, same amplitude, delta p sub m, times the sine of omega 2 t. So the only difference is the frequency. If we use the trig identity that sine alpha plus sine beta is equal to 2 times the cosine of alpha minus beta divided by 2 times the sine of alpha plus beta divided by 2, we can then rewrite this delta p of t is equal to 2 times of the amplitude times a sine, which is the sum of omega 1 plus omega 2 divided by 2 times t. Omega 1 plus omega 2 divided by 2 is the average of the frequencies, but the average is between 30 and 31 Hertz is very similar. It is the cosine term, which has the omega 1 minus omega 2, that gives us the beat. And the beat frequency is this difference between omega 1 and omega 2. If we look at this cosine curve on the graph, this is the yellow curve that just appeared, we see that from 0 to 1 second, it goes from being positive 1 to negative 1. But the beat looks very much the same because the high frequency oscillations of the sinusoidal term go from 0 to 1 many times, while the beat varies very slowly. So whether the beat is at plus 1 or minus 1 doesn't really matter, because you're multiplying by a plus or minus 1 of the sinusoidal term. So the beat frequency is actually the difference between omega 1 and omega 2, not that divided by 2. So it's 1 Hertz. That's why the beat goes from, it has a maximum at 0, and then again at 1 second, and again at 2 seconds, and so on. Let's tune piano. There are 2 adjacent keys on the piano, middle C and B. They have frequencies of 261 Hertz and 246 Hertz respectively, if the piano is properly tuned. If these keys are struck simultaneously, what is the beat frequency? Well, the beat frequency is the difference of these 2 frequencies, so it is 15 Hertz. Why don't you notice this beat? Well, the beats occur every 0.067 seconds, which is too fast for your ear to distinguish the beating pattern. However, the piano is mistuned, so the B key has a frequency of 259 Hertz. Then we get a beat frequency of 2 Hertz, and the beat occurs every half a second, which is easy for your ear to distinguish. If we translated this to another part of the piano, where the frequencies were reduced by 100 Hertz, how would this change beat frequency? There's no change. The frequency difference remains the same, so the beat frequency is unchanged.